Hi everyone, welcome to my presentation on G2D, boosting multimodal learning with gradient-guided distillation, which has been accepted as a poster for ICCV. So here is the outline of my paper. I'll be going through each of these sections gradually. So what is multimodal learning? Multimodal learning builds models that process and relate information from multiple data types or modalities. The goal is to create a more comprehensive understanding, much like how humans use sight, hearing, and touch together. The figure on the right shows a traditional multimodal pipeline. At first, we encode the features of the different data modalities. We then pass it through a fusion module to combine the features, and then those features are passed through a classification head to retrieve the predictions. What is knowledge distillation? Knowledge distillation is a technique where a compact student model learns from a larger teacher model. It transfers knowledge through logics, features, or intermediate representations. The figure on the right shows how knowledge distillation works. Typically, you have a teacher model, which is a pre-trained teacher model, and you have a student model, which you want to train. You provide the training data to both of them. The teacher model is used for inference and to get the predictions. The student model is being trained and it also generates predictions, and the predictions of the student model is aligned with to not only the ground truth labels of the dataset but also the predictions of the teacher model via loss functions. This is how the student model tries to learn from the teacher model, and that is what knowledge distillation is about. Now, knowledge distillation was typically used for model compression. However, nowadays it's being used for complex multimodal tasks like cross-model knowledge transfer and also handling missing data. In our case, we'll not be using it for any of these purposes. We'll be using knowledge distillation to solve a problem called modality imbalance. So what is modality imbalance? It is a problem when one modality often contains stronger signals or learns much faster than others. This phenomenon is modality imbalance, or some people also call it modality competition, and it causes the stronger modality to dominate the joint training process. What are the consequences? The weaker modalities remain underutilized, and this leads to suboptimal performance for the overall multimodal learning model. Here is an example from the CREMA-D dataset, which suffers from modality imbalance. So here there are three plots. The first plot shows the audio performance, the second one video, and the third one multimodal. The y-axis shows the accuracy, the x-axis shows the number of epochs. So first we'll go through the audio performance where it doesn't suffer from modality imbalance. Here you can see that the audio only model, which is a model that has been only trained in audio data, the red curve, reaches an accuracy of 60%. Now, the audio in multimodal model also achieves an accuracy of 60%, and our G2D method also achieves an accuracy of 60%. So this is the dominant modality, and as a result, this doesn't suffer from any modality suppression. However, if you look at the video performance, you'll see that the video-only model, which is a model that has been only trained using video data, has an accuracy of 72%. Now, if you look at the video in multimodal model, it it performs very poorly. It has an accuracy of just 30%. So we see that this modality is getting suppressed in a multimodal setting. However, if you look at our performance, video in G2D, you see that we easily get the performance of video-only model, which is what is expected. And this results in a better performance for us in multimodal setting. We achieve an accuracy of 83% on CREMA-D dataset, whereas traditional multimodal models, as the video modality is suppressed, get a performance of just 62%. So this is the problem, which is called modality imbalance. So how do we do it? We create a framework that mitigates this imbalance, and we introduce two key ideas. The first one is knowledge distillation, where we transfer knowledge from expert unimodal teacher models to a single multimodal student model. And then we introduce a dynamic modulation, gradient modulation strategy, which is called sequential modality prioritization, or SMP, where we give each modality, especially the weaker ones, a dedicated turn to lead the learning process. So as I've talked earlier in the plot before, we've seen that our method successfully mitigates imbalance. And you can see that in the third plot over here. Now I'll be going through some of the related works. There has been a lot of work in preventing modality imbalance or mitigating it. There has been some gradient modulation techniques. Popular methods include OGMGE, which is on-the-fly gradient modulation with generalization enhancement. There has been work with AGM, which is adaptive gradient modulation, and also modality-specific learning rates. There also has been some feature balancing and alternative training methods like MLA and PMR. However, for most of these methods, they introduce dedicated hyperparameters, and we need to extensively tune these hyperparameters to different datasets, limiting their generalizability. In our case, we don't have this, we don't require this extensive hyperparameter tuning because in our case, we use KD with SMP and we use the robust signals from unimodal teachers, and those robust signals from unimodal teacher dynamically guide the training process, removing the need for extensive manual hyperparameter tuning. So this is our figure. This is a complete overview of our framework. We use pre-trained unimodal teachers. So this is for the framework assumes that we have two modalities, audio and video. So these are the unimodal audio and video teachers on the right. On the left, you have the multimodal student model. This is the G2D loss module. And then we have the scoring module and then the SMP, which is sequential modality prioritization. So how everything works. First, we have the audio and the video data. These are passed to the multimodal student model and the unimodal audio and the unimodal video teacher as well. We get features and logits from the student and the unimodal teachers. We pass it to the loss function, which is the G2D loss module. Once the loss is calculated, the gradients are calculated for the unimodal encoders of the multimodal student model. On the other hand, we take the logits from the unimodal teachers, gather the scoring, use the scoring module to calculate confidence scores. These are then passed to the sequential modality prioritization module. This module basically decides which modality to focus on and which modality to suppress. Once that is done, we multiply the modality coefficients with the gradients of the unimodal encoders and then pass it to the multimodal student model. So in this way, we prevent modality imbalance. I'll be going through each of these sections one by one, starting with the G2D loss module. So the G2D loss function has three loss functions. First one is the student loss. This is a standard supervised loss. It maps the student's final multimodal prediction to the ground truth label. Then we have feature loss. It aligns student and teacher features for each modality, preventing weaker modalities from being ignored. And finally, we have logit loss. It uses scale divergence and it aligns the output distribution of the student with each of the teacher's logits, transferring class relationships. So this is the final loss, which is a weighted sum of the three components, the student loss, the feature loss, and the logit loss. Alpha and beta are weighting coefficients. We kept it both to 1, and that gave us the best performance, as you will see later. So now we are done with the G2D loss module. Next, we'll focus on how the framework dynamically balances modalities, starting with the scoring module. So before talking about the scoring module, we need to know a basic understanding on what confidence scores are. So the plot shows the confidence scores of 3 datasets. The left figure shows it for CREMA-D, the middle one shows it for AVM-NIST, and the right one shows it for UR-Funny dataset. CREMA-D and AVM-NIST are two modality datasets. Now, if you look at the confidence scores of the teachers, you'll see that audio, which is the blue line, is consistently more confident than the video teacher. For AVM-NIST, you see a reverse picture. You see the video teacher is consistently confident, more confident than the audio teacher. And for the UR-Funny, it is a 3-modality dataset. And over here, you see the text teacher, which is the text modality, when trained only using textual data, is consistently more confident than the audio and video teacher. So this shows that datasets are biased towards one modality. When you collect datasets in the wild, naturally, one modality would be more useful to the model than the other modalities. And this is where the modality imbalance happens when you start training multimodal models. This motivated us to actually solve the problem using confidence scores. Now, how are confidence scores calculated? It is nothing but the batch-wise average probability assigned to the ground truth label. So if there are 3 classes, And for each sample, you know the ground truth label. You basically get the probability assigned to the ground truth label, and you do it for all samples in a batch. You sum them up, divide it by the number of samples, and that is what is the confidence score for the model per batch. So now we know how the confidence scores are being calculated. Next, the confidence scores are passed to the sequential modality prioritization module. This module, or SMP, is a four-step process to mitigate imbalance, and we hypothesized the hypothesis 1, which states that leveraging the confidence scores of unimodal models to determine less confident modalities and sequentially prioritizing them during training can mitigate modality imbalance. And we later show in the results section that this hypothesis holds true. And the confidence scores plot inspired us to propose this hypothesis. So the four-step SMP is basically starting with ranking the modalities. We first rank them, where pi t1 basically denotes the least confident modality, and pi tk, if there are k modalities, denotes the most confident modality. So step 2 is prioritizing them. The prioritization schedule MQ basically states that for the first tau 1 epochs, only prioritize the least confident modality, which is pi t1. For the next tau 2 epochs, only prioritize the second least confident modality. Let us assume there are three modalities. So we've already prioritized the weakest and the second weakest modality. Then that leaves us with the strongest modality, which is pi t3. Now, for the strongest modality, we don't prioritize it. What we say is, since it is the strongest modality, it dominates the training process, train it together with all other modalities for tau j or tau 3 epochs. So when I mean by prioritization, what do I mean by prioritization? So this is where gradient modulation comes in. We have a modulation coefficient, k kappa mq, which acts as a gate. It turns on the gradients only for modalities currently prioritized in the prioritization schedule m subscript q. So when I say that for the first 50 epochs, prioritize the weakest, the least confident modality, I basically mean that only allow the gradients to flow to this modality and prevent the gradients to flow to all the other modalities. How do I do that? We do it using the modulation coefficient. We basically assign 1 and multiply it to the gradients so that the gradients can flow to the least confident modality, and we make the gradients of all other modalities 0. And how do we do it? We do it using step 4, which is updating student parameters. So we calculate the gradients for the encoders, for the unimodal encoders of the multimodal model, and we multiply the gradient modulation coefficient. So if it is 1, the gradients are allowed to flow. If it is 0, we prevent the gradient flow. So in this way, we prioritize the modalities. So this is the complete G2D framework. The student learns via the G2D laws, guided by the stable teacher confidence scores that drive the SMP mechanism to ensure balanced, interference-free training. We evaluated G2D on 6 diverse real-world datasets. Here are the datasets. We also did it for a regression task and 5 datasets on classification. So these are the backbones we've used. We've used ResNet 18 for audiovisual datasets, Transformers for audiovisual and text datasets, and MobileNet V2 for the regression task, where we used MobileNet V2 for image feature extraction. And for the tabular data, we've used FCN, or fully connected neural network. These are the training and hyperparameters. Now, if you look at the results, you will see that modality imbalance is dataset dependent. On CREMA-D, the video modality is suppressed, while on the AVMNIS, the audio modality is the weaker one. So what do I mean by this? So on CREMA-D, we know that the video modality is suppressed by looking at the confidence scores, and we see that while normal multimodal learning, the video modality achieves an accuracy of only 27%. However, if we look at the video performance of CREMA-D when trained only using video data, it achieves an accuracy of 76.5%. So this shows that the video modality is being suppressed. On the other hand, AVMNIST has the reverse case. We see that the audio modality, when trained in multimodal model, achieves only 16% accuracy, whereas if the audio data is trained separately in a unimodal setting, it achieves an accuracy of 42% or around 43%. So we see that which modality will be suppressed or which modality will be dominated is completely dataset dependent and cannot be known beforehand. That is why we use confidence scores of the unimodal teachers, and that is why our method is dynamic. And if you look at our performance, you'll see that we surpass all baselines, and we also outperform the competing KD-based method, which is UMT. These are the results for 3-modality dataset, which is You Are Funny, and you will see that G2D excels in 3-modality settings as well. Another interesting thing to note is we avoid modality depression, where other methods oversuppress the dominant modality. So for You Are Funny, as if you recall, text is the most dominant modality, and you see that the text modality has an accuracy of 58%, but other methods oversuppress it in order to balance the other two modalities. But in our case, we don't oversuppress it. We have it to its actual accuracy, which is 58.2. Now we also evaluate it on our regression task on the MISME dataset, and we see that our method performs the best. We have the lowest MAPE, or mean absolute percentage error, and the highest R square. So now these are the analysis that we've done. We've first analyzed the feature alignment, whether how well do the students' feature match the teachers. We measure the cosine similarity between the students' features and the expert unimodal teachers' features on the Cremati dataset. We show that feature alignment for both audio and video is consistently higher with G2D compared to joint training. So you see that the cosine similarity of G2D, which are the orange dots, are comparatively higher than joint training, which are the blue dots. So we see that we achieve improved feature alignment through G2D. The next is the confidence ratio. We define confidence ratio to quantify how much a weak modality is suppressed. It measures the modality's confidence within the multimodal model, normalized by the score of its expert unimodal teacher. So a higher ratio basically indicates that the weak modality is performing near its full potential. A lower ratio indicates that it is being suppressed. So if you look at the bar plot, you'll see that for Crema-D, the light blue plot, which is joint training, this is the confidence ratio of the weak modality, which is video. And you see that it has a confidence ratio of just 0.36 under normal multimodal learning. But in our case, we have a confidence ratio of 0.96 for the video modality. So this shows that we clearly reduce the problem of modality imbalance. For AVM Nest and VG Sound, we see similar cases. We achieve a higher confidence ratio compared to normal joint training. And this demonstrates that our method effectively mitigates modality suppression and ensures a more balanced optimization process. Now we'll be going through the modality gap. This analysis was initially shown by Liang et al., and they show that larger modality gap or more distinct embeddings often correlates with better performance. And this is also true for our method. We show that when the gap distance is higher, our method also performs better. So if you see for AVM NIST, the joint training has a gap distance of 0.13 between the audio and video features. For us, it's 0.17, which is an increase, and therefore we also get better accuracies. For You Are Funny, we see a substantial difference. For You Are Funny, joint training has a gap distance of 0.17 between the visual and textual features, whereas in our case, we have a gap distance of 0.71, which is basically highlighting the fact that gap distance aligns with performance. Now we'll go through some of the ablation studies. So we've introduced a dynamic gradient modulation strategy, SMP, and this SMP has universal benefit. It can be applied not only to our G2D loss module, which uses distillation, but it can be applied to all other methods. Now, if you apply SMP to any other method, it might be joint training, it might be UMT, you see that their performance improves when SMP is applied. However, when SMP is applied to our loss module, we get the best performance. Now we do an ablation on the fusion modules. There are various fusion modules: summation, concatenation, film, bigated, cross attention, and late fusion. We observe that late fusion performs the best or gives us the best performance, followed by cross attention. We also do an ablation on modality suppression. So in our case for SMP, by complete suppression, we mean that we either make the gradients 0 or 1. When a modality is prioritized, its gradients are allowed as it is. The gradient modulation coefficient is 1, and all other modalities are completely zeroed out. The modality gradient modulation coefficient is 0. That is what we call complete suppression. partial suppression, which was introduced in OGMG, we also tried it in our method, where instead of completely zeroing out the gradients, we use a fraction of it. And we see that this doesn't work as well as our method, where we completely suppress the other modalities out and allow the weak modality to train in isolation. And this works better. Now we also do another ablation on the effect of prioritization epochs. So tau j is the number of epochs the weak modality is trained in isolation. I mean, the gradient of other modalities are made zero. So if you look at CREMA-D, the first column shows that this is the accuracy for only using G2D module without SMP. The second column shows that we use SMP, but only for the first 50 epochs, where the weak modality was trained in isolation only for 50 epochs. And then the next column shows it for 100 epochs and then for 150 epochs. So we see that as we increase the number of epochs where the dedicated training epochs for weaker modality is increased, it improves performance. And the same is seen for the IMO cap dataset. It is a 3-modality dataset. So the first one shows using only G2D loss module and training it for 150 epochs. The second one shows where we train for the first 50 epochs the least confident modality. The next 50 epochs, we do it for the second least confident modality. And for the next 150 epochs, we train all modalities together. And the same case goes for the 75, 75, 150. And we see that as we increase the number of epochs for the weaker modalities to be trained in isolation, the performance improves. And this validates our hypothesis 1, which states that interference-free training time for weaker modalities is crucial for mitigating modality imbalance. So here is the conclusion of our work. We addressed the challenge of modality imbalance in multimodal learning. We introduced a novel framework, G2D, that combines gradient-guided distillation with sequential modality prioritization to ensure all modalities contribute effectively during training. We outperformed 10 state-of-the-art baselines across 6 diverse datasets, including both classification and regression tasks, and we've successfully mitigated modality imbalance. This work holds great potential to advance balanced learning in complex multimodal scenarios, paving the way for more inclusive and robust AI systems. Here are the references, and I would like to thank you. And if you have any questions, I'll see you at the poster session.